Right. Hey, let's try another video solution. And how about going back here to chapter 31, number 64. I was asked about this, and of course this is Faraday's law here. And I thought it would make more sense to print the picture ahead of time here so that I can point out a couple of things here. Number 64 is a magenta one, so it is definitely a hard one. It also says a review problem, as you'll see, because half of this problem, and maybe more, really goes back to Physics 121 and motion here. Watch, let me just read it here. It says a bar of mass little m. So here's this kind of this turquoise bar here, mass little m, is pulled horizontally across parallel frictionless rails by a massless string. So here's the string, and you can see it loops around to a weight of capital M. That is attached to a suspended object of mass capital M. A uniform magnetic field has a magnitude of B, and the distance between the rails is L. So you can see from rail to rail where this bar lays across is L, and of course there's the M, and it's going to pull this across. And this would be a fun mechanics problem alone, but we have a uniform magnetic field in here. Okay, and hopefully what you see in this problem is the electromagnetics, not just the mechanics. I mean, obviously, gravity is pulling it down, and then there will be a tension in the string, and the tension will pull this bar, and that's all the mechanics stuff. But the new stuff, the electromagnetics, is we have a loop here. We have a rectangle with some resistance R. And so as this bar moves, the flux through this rectangle increases. And so therefore, as a change in flux, and a change in flux is going to make an EMF. And so there's going to be an EMF established. And I'm not sure which way. I keep drawing this kind of a counterclockwise, but I really don't know at this point whether it's going to be clockwise or counterclockwise. But your author been writing the current, I think, in purple. Can't remember now, but nonetheless, I will and figure out what direction the current is. But I better finish reading the problem. It says here, the only significant electrical resistance is the load of the resistor R. Okay, so now when it comes to the electromagnetic stuff, we are going to get an EMF, there's going to be a current, and the whole resistance around the loop is really all in this little section right there. They're saying this is all negligible, and the resistance would be capital R. It says here, derive an expression that gives the horizontal speed of the bar as a function of time. Assume that the suspended object is released with the bar at rest at time t equals to 0. All right, so again, maybe doing forces in I don't know, maybe a blue color here. We certainly have gravity pulling down, mg. We have tension pulling up. That would be the free body diagram for capital M. And for little m, it would be pulled horizontally with a tension of T. And they said there's frictionless or negligible friction, so we don't have to worry about that. But there is another force, and that is the current. So let's figure out which way the current is, because I'll say it again, here's the conceptual side, that as this bar is moved up, there's more flux. And so therefore the change in flux. And Lenz's law says it opposes the change. So as the bar moves to the left here, this more flux means that the secondary flux, the flux made from this secondary one, is going to make it go down to oppose the change. And so if I point my thumb down and take a look at my fingers go around in a clockwise direction. And so there would be a current I, kind of drawing in pink, going from front to back in this bar, and then left to right, and then back to front through the resistor, and then right to left over here in this front piece. And so there would be the loop of current. And of course, what's relevant here then is now that we have an induced EMF, which made this current, we now can say there would be a current in a magnetic field. And so here's where the equation F I L cross B comes into play. And so I guess that takes us back to chapter 29. But it's a cross product, so I'll use what I've been calling the first right-hand rule. And that is if I put my fingers in the direction of the current and then close towards the field, which is up, my thumb is pointing then to the right, and so that would be the magnetic force. Maybe I'll even put a sub B right there, and so there's going to be a magnetic force opposing its motion. And of course, I did what I'll call the official Lenz's law. Maybe you guys caught in another video answer I did, there's what I call the cheater's Lenz law. And we know that no matter what happens in this very complicated bit of flux and direction and right-hand rule, that we've got to oppose the motion. Not just oppose the flux, but also oppose the motion. Because if it was the other way around, if, say, this force was in the direction it was moving, then that would make it go even faster and faster and faster and faster. And, of course, there would be no limit to it. And where does it get that energy? And it would just be in a violation of conservation of energy. So if everything works out right and we do Lenz's law correctly and look at the change in flux, we should get a current and then eventually a magnetic force that opposes the motion. And like I said, we could have done the cheater way of Lenz's law and realized that right from the beginning, that there is going to be a magnetic field towards the right because it has to oppose the motion, which is the tension in this cord, which is pulling it to the left. All right. With that conceptual idea in mind, and I'll come back to the picture if we need it, let's start writing out our equations. And so, as I said here, number 64, the first part of this and why it's called a review might be to just do a free body diagram for the hanging mass, the capital M. And so there's a force of mg pulling it down and a tension T pulling it up. Whereas the free body diagram for this rod that is kind of a turquoise, maybe even a sea green, I don't know, in color, would, of course, have the tension pulling it to the left here, as we talked about, but then there would also be a magnetic force pulling it to the right. I guess technically there would also be a weight pulling it down of little mg, but then there would be the normal force. We're not going to need those unless there happened to have been some friction where then there would be a frictional force. And the frictional force is the coefficient of friction times the normal. That would have been a little harder problem. It's already a hard problem, so the author made it a little bit easier by saying there is no friction, so we can erase that. And because of that, we don't need to know the normal force, and because of that, we don't need to worry about the vertical forces. So just to be a little complete with my free body diagram, I'll do all four forces, but then just focus on the sum of the forces in the x direction. And so if we call the left the positive direction, since that's the way it moved, we would have t minus f sub b equals little m times a. And so there is, maybe I should put it in the line above, Newton's second law. And so going all the way back to chapter 5 of this class, the sum of the forces equals ma. So in this case, left and right, there's two of them, and that equals 2ma. And I can do the same thing here. I can call down mg, and I'll call it positive, so it'll match with the positive here. So when this one goes down, this one goes left. Minus the tension equals then ma, and then those are capital M's. And so again, at this point, I would say I've really only done Physics 121. Obviously, this class comes in right there about how much force is there. But I think I will then combine these two equations together, but by maybe saying right here, the tension is capital Mg minus capital A. So that over here, I could put capital G minus capital A, for the tension, subtract the magnetic force, and equal to the acceleration of that little object, the rod here. And so ma. Now is where maybe we want to combine and do this current chapter. Well, maybe it's a little early. I'll just leave it the way it is. Nah, those each have an A in them, so I'm going to move them together. So what I have is mg minus the magnetic force. When I move this over to here, it becomes little m plus capital M times A. And so now we're at the point where we need to give this some thought. And we wrote it out here. This takes us back to chapter 29, that the magnitude of it would be the I, the L, the B, and the sine of the angle between the current and the magnetic field. And in this case, the magnetic field is pointing up and the current is going back, and so they're at 90 degrees. So this is just I, L, B. And for this problem, the L being the length is a lowercase l. So maybe for this problem, I ought to put, instead of a capital L, a lowercase l to match. And in fact, most of our electromagnetics, we like to use the lowercase l because as you're learning here in chapter 32 and beyond, capital L is the induction symbol. So the inductance, we like to make sure we don't confuse it with L. Anyway, so that's probably a better way to write it. And then, of course, also in chapter 20, I said that was 29. I think that's right. Yeah. And I started to say also 29, but it's not also. It's back in 27, we learned Ohm's law, that the current would be voltage divided by resistance. Now, in this case, the voltage is created by an induced EMF. So let me write that as the script E. And then maybe I'll put the L and the B and the R over here. And then, I'll just do the script E. But now finally we get to something related to this chapter, which is the Faraday's law, which says that the magnitude, and this is really magnitude, I already dealt with direction and all that back here in the sign. So the magnitude of the EMF is the number of turns times the change in flux. And for this particular problem, we only have one loop, so capital N is just equal to 1. And then the flux would be the area, and this is just our standard motion EMF. But I'll derive it again. I've done it a number of times, but it's worth seeing it again. If we called this distance out here to the bar x, then the flux, which is B dot dA, would then become the strength of the magnetic field times the area. And the area is changing, but not the magnetic field. So I'll pull that magnetic field in front of the derivative, and so I get a B. Then I got the derivative of the area. The area is made up of its length L and its width, what I've called X. And the one that's changing is the X. So I can then take that L and also pull it out. So that becomes an L squared over R. And then I have the derivative of X with respect to time. And that is just how is this thing moving in the X direction. That really is the velocity. So there is the magnetic force. I guess I didn't put equals all the way down, but this is what the magnetic force is equal to, after we put together chapter 29, chapter 27, and then this chapter 31, Faraday's law. All right, so this is what I was looking for. Okay, so like I said, this step right here, from here to here, really is the chapter 31. The rest of this is earlier chapters. And especially this stuff. This is not only just an earlier chapter, this is an earlier semester. Okay, so then I have this mg, and now I can put an L squared B squared over capital R for resistance, and then velocity, and then little m plus big M, and then A. And this looks a lot like chapter 6, where we had air resistance, right? We had gravity pulling it down, then we had something opposing its motion. And in the case of air resistance, when it was slow, it was linear to the velocity. And we also had it proportional to the square of the velocity, but this would be the slow motion. And that's exactly what this looks like. So, and then equals to total mass over A. And so this is exactly chapter 6. If you recognize it, great. If you don't, that's fine too, because hopefully what you do recognize is that it is a differential equation, because if we're asked to find for velocity, then we should probably write acceleration as the derivative of the velocity. So now we have an equation that only has velocities in it. And I was helping somebody not too long ago, and I told them that, you know, don't sweat too difficult of differential equations. We don't give you anything in this chapter that isn't separable. That is, you can put all the variables, in this case, all the v's on one side and all the t's on the other, because those are the easiest differential equations. You don't have to have Math 220. You just have to have Math 160, where you've learned and saw these simple differential equations. When they're separable, again, you just put one variable on one side, which in this case, I'll put the v's over here on the right-hand side, and I'll put the t's on the other side, and then you integrate. And then you've got your, you know, just t's on one side, so it becomes an integral, and you have your v's on your other side, so it's an integral with v's. And then, of course, then you have velocities and time, and then you can, you know, solve for velocity equals. And that's what we're going to do. And that's fortunately what we have in this one. So to make it work, we probably should divide both sides by mg minus L squared B squared R over V. So mg minus L squared B squared over RV. So that over here on the left-hand side, we got just the number 1. And over here on the right-hand side, we were able to get our V's together, or at least we were able to get that V together with the D V, page 1. Maybe I should have put one, page 2. Actually, we started with this picture, so it's page 0 and page 2. But moving on here to page, whatever you want to call this, page 3. Then it's the easier step, just bring the dt over. So I would get dt over here on the left-hand side, and little m plus big M all over big M minus L squared B squared over R V D V. Yay! Okay, so now I have a good place. It's still got a little bit of work to do mathematically, but now I can just integrate both sides. And this is that tricky move with the integral. Let me put the limits as from 0 to t. And I'm going to use then the limits as a variable, which is a little bit maybe new for some of you been thinking, and I hope I explained this in one of the other videos, that you don't have to put a number. I mean, if we wanted to know the speed after 5 seconds, we would go 0 to 5, and then we'd come over here and say, well, what is our starting speed? 0, and then we would, you know, put like v maybe sub 5, meaning this would be the velocity after 5 seconds. So maybe it's better just to put a v over here and a t over here, because then if we just do the integral, we would have a t in our answer, and we could put whatever number we want. It doesn't have to be 5 seconds. It could be 3 seconds. It could be 10 seconds. We could be whatever number we want. So it's nice to put our limits that way. So we go 0 to t. So this would be t evaluated from 0 to t. And like I said then, this just comes out to be a t. But again, what's really nice about it is I don't have to specifically say this is 5 seconds or 3 seconds or 10 seconds. I can do that later on when I go to ask this question. And they don't even ask for a specific time. They ask for an equation of time. So they really want me to do that, to leave it as some function of time. Okay, now on the other side of the equation, this is a u sub. But maybe it's a little too complicated to see that, so why don't I call u equaling this whole mess? Mg minus L squared B squared over capital R times V, so that du, that looks more like a mu there, let me fix that, du, so it's a u. So du equals, and we don't need to worry about that one, but we would have the L squared, the B squared over R, and then we would have the dv. So when we do this integral, of course we still have the little m plus big M in the top, but this whole thing would be then a u. And the dv then, if we move everything to this side, I don't know if I gave myself quite enough room. Let me go to the next line. So little m plus big M, and then there's the u downstairs. And then I would bring the negative over with the r. I would bring the L squared and the B squared downstairs. And then there's the du, and then all of that is just equal to dv. So there's my substitution of dv. And so this is why I'm saying this is a perfect u sub, because the negative in the r and the little m plus big M are constants I can pull out. The L squared and the B squared are also constants that I can pull out. And then I just have the du over u. And that's an easy integral that you're familiar with. And in fact, to make my life maybe a little bit easier, I'm going to move all of these constants together with the time. So I'll move the negative over. I will have an L squared and a B squared in the numerator when I move it over with the t, but I'd have an R for resistance and a little m plus a big M in the denominator. That then would all equal to this integral, and as you know, the integral of du over u is ln of u. And I think I mentioned this a number of times. I don't like to mess with my limits for the u because I like to just go back to, well, what is u? Well, remember u way back here was this mg minus the L squared B squared RV. So I can put my limits in terms of my v. And so I never bothered to figure out what a 0 for v would be my limits of u, although I guess it would be really easy. It would just be mg. So if I did put my limits, it would have been mg, and then this limit would have been mg minus L squared B squared RV. But I find it easier to just go back to the v and put it in for the u, and go back to my limits of the u to a v. And so, now that, I mean, they're really essentially the same, so I guess it doesn't really matter which way you want to do it. So this would be ln, and so if you put in a v, you get mg minus L squared B squared over RV minus ln, and if you put in 0 speed, you get mg. And of course, another neat thing about logarithms is a difference is the same as a quotient. So we can take the difference in our logs and write it as a quotient. And now we can get rid of our natural log by raising everything to a power of e. So the left-hand side becomes e to the negative L squared B squared T over R little m plus big M. And this side, of course, gets rid of that, so it becomes big mg minus L squared B squared over RV all over mg. So I told you there was a lot more math to do, even though way back here I was like, okay, we're kind of done with our physics once we put that in there, but now we got to solve all this math. So on to page 4 here. If I bring the mg over here, I get mg e to the minus L squared B squared T over R little m plus big M equals mg minus L squared B squared over R times V. Okay, so now if I want to get this solving for V, why don't I put the L squared B squared over RV over here on the left-hand side. And then over here I'll put the mg, and then this will be a minus an mg e to the minus L squared B squared T over R little m plus big M. And of course you can see that each one has an mg in it. So let me first factor out the m and the g there. And then, of course, I can bring the r over and also divide by the L squared and the B squared. And I'm left with just the V. And that's what the problem said. Solve for the velocity. And hopefully that's what the author got. In fact, let me just look real quick. Let me call it up here, mg. Okay, good. And then minus, oh wait, he's got a B squared. Oh, there, he just lists that first. Okay, and it matches. Hope that helps.